So in these first examples, we're just going to take a look at some elementary school versions of reducing fractions, and then also look at the high school version, which is reducing a rational expression. There's a lot of similarity, and that similarity is really important to understand. So when I look at the first problem, when I look at the first problem here, what I'm going to do is I'm going to demonstrate why using multiplication tables is a more efficient way to divide. Again, many of you learn to reduce this in elementary school by doing this. But I want to appeal to your sense of algebra balance. Does it make sense to divide and then reduce division by using two additional division signs? So yeah, it works, but it's probably better to understand it as a problem that compares multiplication facts. This is 1 times 3, and this is 2 times 3. And then what we're going to be looking at is the fact that the 3's cancel out, and that's what causes this fraction to reduce to 1/2, right? It's not because we divided anything, it's because we examined the product, and the product cancels with the division symbol. If that makes sense. That's balance in algebra, right? Division should cancel with multiplication, not division cancels with more division. So the reason that's important is that's exactly how you do this in high school. You can't come over here and divide by 3. That doesn't make any sense. So what you do is you factor this expression, right? The factors of 3 that are going to add up to give you 4. That would be 1 and 3. And we would come over here and we'd say, okay, this is x plus 1 and x plus 1. Notice the reliance on multiplication facts in factoring, and how that's exactly like this problem worked out in elementary school if you were taught the multiplication fact way of reducing fractions. So when I look at the denominator, same thing happens here. We're going to start with 6 and move this way. We're again going to use 2 times 3, so it's virtually identical to this over here. And so what we get is we get x and x, and then we put our 2 and our 3 in, so 2 and 3, and you can already see the common term that is happening. So this term right here is common and can be removed because this divided by this is actually 1, meaning it cancels. 1 is the number in algebra that indicates something has reduced when you're talking about multiplication or division. Another way of saying that is it is the multiplicative inverse number, right? The inverse property. So this comes out to x plus 1, and the denominator comes out to x plus 2. And then we have to return to a concept that we saw earlier in the year, because this is the correct answer, but this problem has domain restrictions. So what are those things, right? So this is our answer, but the answer must include, usually use a little semicolon, and then say, well, this has domain restrictions at any place in the problem that ever had a 0 in the denominator. So the easiest way to do it, to find your domain restrictions, is simply set the two denominators you started with, x plus 2 not equal to 0, and then x plus 3 not equal to 0. And this is exactly like finding, in previous units we found the solutions or the roots or the zeros. These are like finding anti-solutions, right? You cannot ever have -2, and you cannot ever have -3 be a part of the solution. So the process is very familiar to us. You're using the zero product property again, but you're using the zero product property to find where the equation cannot equal 0. And then you'd want to put them in order, so -3 and -2. Again, how did I find the domain restrictions? I set the denominator not equal to 0 and found the places that would cause the problem to be undefined. So it's pretty obvious that -2 is undefined, because if I plug it back in here, it's going to give me a 0 on the bottom. But -3 was a domain restriction before I canceled it, and you cannot cancel out domain restrictions. Later on, when we do graphs, you'll see why. So those domain restrictions, when we do graphs, they later become things that have different names, and you'll understand why the -3 actually did not disappear. All right, let's take a look at another one. So down here, we have, on the elementary school side, we have a 12 and we have a 20 on the denominator. So we ask ourselves, what do they share multiplication fact-wise? Well, both of these problems share a 4. This is 4 times 3. And the denominator shares a 4, but it's 4 times 5. And so this will cancel out, leaving us with 3/5. Okay? That is exactly how we will do the next problem in algebra too, but you notice that, oh my goodness, they wrote it backwards. So quite frequently in this chapter, they really start focusing students on standard form, because remember, the definition of a rational expression is that it is two polynomials, in this case, two quadratic trinomials. But understanding that, we learned in the polynomial chapter that we had to put things in standard form, they like to try to stress that again here. So the bottom was in standard form, the top was not. And so now I'm going to begin factoring the top by taking out the GCF. Remember, the smallest GCF that ever has to be removed is a -1. So this is actually going to take me 2 steps to do the numerator rather than just 1. So if I take a -1 out here, remember I'm just dividing, right? Just dividing all these by -1. This will be positive x, and this will be -12. And then on the denominator, I guess I could go ahead and factor it, but just for consistency, I'm going to just leave it unfactored so that you see the factoring in the next step. Okay, so here we go. Here we will get on the top, pardon me, we're going to get 3 and 4, just like we got over here, but we just do it a little differently in algebra. We're going to have a 3 here, a 4 here. We want it to be positive in the x, so this one will be positive, and this one will be negative. -3 and 4 make +1. The x's come from putting the x's here. And then here, we're going to have the same thing. In fact, it uses the same numbers as over here. It's going to be 4 and 5. So I'll go ahead and put my 4 and my 5 here. And then what happens is we're trying to get -1. So this actually is negative, and this will be positive. And then the question is, what cancels? They don't have to be right over top of each other like they were in this example. As long as you have 1 on the numerator and 1 on the denominator, they cancel out. So our final answer is -1 x minus 3 divided by x minus 5. And quite frequently on a standardized test, they would actually go ahead and distribute that negative back in the numerator and give you -x plus 3 divided by x minus 5. However, we have not completed the domain restrictions. So how do we do that? Well, I always like to do it at this step right here, because even though I canceled it out, again, that's going to have a name later on a graph. So we can't really get rid of it. We just set them not equal to 0. Again, we're finding the opposite of solutions. We're finding unsolutions, or whatever you want to call them. But it's the same process. We are using the zero product property here. So x cannot equal -4, and x also cannot equal +5. And I need to include them in my answer right here, right? So I need to say, this is my answer. However, x cannot equal, and you just put them in order, it cannot equal -4 or 5, because if you can clearly see if I put 5 right here, I'd get a 0. But earlier in the problem, if I put the -4 in this step, it would also cause it to fail. So you need to make sure you include those domain restrictions. They are part of the answer.